All right, good morning. This is College Algebra, February the 5th. A couple of things to talk about. One thing I do not have written here on the screen right now that I'm going to go ahead and write right now. But remember, you do have WebAssign homework due on February the 11th, and you will have WebAssign homework due pretty much every Sunday the rest of the semester. Typically, I'm going to make it due Sunday evenings at midnight, and that's going to be pretty regular. So please try to keep up with the WebAssign homework. Let's talk a little bit about Exam 1. So the window for Exam 1 opens February the 8th and runs through the 13th. So remember that you take the exam at any of the testing centers in the Lone Star system. You don't have to necessarily make an appointment, but you do need to check the hours that the testing center you're going to use are open the day that you're going to take the test. Any date from February the 8th through the 13th, you can take the test. And I'm going to send you several remind messages later in the week to kind of keep you up to date on how that goes. So please start paying attention to the exam window. Think about when you're going to be taking the test, what testing center you're going to take the test at. Please make sure that you have a photo ID with you when you are ready to take the test, and keep that with you when you go take it, so because they're going to check that at the testing center you go to. The time limit I'm going to put on the test is going to be 2.5 hours. That should be easily enough time to take the test. It should actually take you a decent amount of time less than that to take the test. So just kind of think about that, but that shouldn't be a concern for most of you. Graphing calculators are allowed on the test. We haven't really used graphing calculators per se in class at all yet. I will going into exam 2. So over the next couple weeks, we will definitely be bringing graphing calculators onto the videos, and I'll be showing you some screenshots of some things with graphing calculators as we go through the semester. But you can certainly bring either a scientific calculator with you or a graphing calculator, and most of the testing centers have graphing calculators there that they will lend you to take the test. You're not allowed to take any notes in with you on the test, so make sure that you're aware of that. No notes on the test at all. Also, I've had several people asking me this question. Those of you who are not used to the way I do things, but definitely no paper and pencil test, or I'm sorry, no multiple choice test. It's not a test on WebAssign. It's a paper and pencil exam, so you get a test and you're going to work problems, and your work is going to actually be on the test itself. I will have online office hours this week, tomorrow from 11 to 12 in the morning, and 8:30 to 9:30 tomorrow evening, and then again on Sunday evening from 8:30 to 9:30. Remember, you can also make online office hours by appointment. I have had a few appointments so far this semester, and I will continue to do that. So if you email me and we can come up with a time that's mutually agreeable, I can meet you online in my WebEx room, and we can go over some homework or things from the review or whatever you want to do there. And then let's see, Sunday evening again, I'll be in my office from 8:30 to 9:30. Okay, I think I mentioned that. On campus hours, I will be on campus this week. On Wednesday from 4 to 6 p.m. and on Thursday from 9 to 11 a.m. And remember, that's on the North Harris campus. And it is in Winship 115K is where my office is. So don't hesitate to come by. Last semester when I did this, I typically only had 1 or 2 people come by. Those students who came by usually did well during the semester. So don't hesitate to come by. If you have some questions and you want to talk to me face to face, I'd be happy to help you out. Today, I want to go back over even and odd functions a little bit. We did talk about that last time, but I want to make sure that I'm clear on what I'm going to be asking you on the exam on that. And I was maybe a little bit I was a little bit worried that maybe you didn't come out of what we talked about with an accurate depiction of the way the exam might look with even and odd functions. So I want to talk about that just for a few minutes, maybe 10 minutes or so at the beginning of the video. And then we're going to move on and talk about piecewise defined functions, what a piecewise defined function is, and how to graph a piecewise defined function. And then finally, we're going to start function transformations, and I'm going to term this function transformations part 1. And so then function transformations part 2 will come after the exam. Please note that the even and odd functions material I cover today will be on exam 1, but the piecewise defined function stuff and the function transformation stuff will be on exam 2, and so that's where exam 2 will begin. So exam 1 ends after even and odd functions. So exam 1 here, exam 2 there. And then I'll entertain any other questions that any of you who are with me live today have as we go through this and as we finish up class today. All right, so we want to talk about even and odd functions again, and so let me kind of divide this up into 2 columns here. We have even functions there on the left side and odd functions here. So remember, an even function is its graph is symmetric with respect to the y-axis. If you have a function that is whose graph is symmetric with respect to the y-axis, then that is an even function. So if I were to give you some graphs, and so let's say you've got a graph that looks like this, a graph that looks like this one right here. Let's say that this one and then finally this graph right here. So all right, and if I ask you on a test, tell me whether this function is even, odd, or neither, right? And let's not worry about the odd right now, the odd part of it. But in this one, this first graph has symmetry with respect to the y-axis, right? So this first graph is an example of an even function, right? Because that graph has symmetry. I could fold the graph along the y-axis, and the graph would fall on top of itself, right? Or you could just look at it that every point on one side of the y-axis has a mirror image point on the other side of the y-axis like that. So that first graph is even. The second graph is not even. That graph, if I fold it along the y-axis, that graph does not fall on top of itself. The points do not have mirror images on the other side, right? There's nothing on the other side of the y-axis for those points. And so the second one is not even, right? This one is not even. And then this last one, once again, all the points have mirror images on both sides of the axis like that. They all pair up, and so this last one is even. All right, so I want to make sure one thing is that you can tell me by looking at the graph whether a function is even or odd. And then the other thing about even functions is that they have the property that f of x and f of negative x are the same function, that you get the exact same thing for either one of those. So that's if you have a function that's written like this, f of x equals 2x to the 4th minus 3x squared plus 8, right? If you look at f of negative x, then when you put negative x in place of x, every place you see it, notice that every one of those negative x's is raised to an even power. And so what happens there when you raise a negative number to an even power, it becomes positive. And so those terms are not changing sign at all, because negative x squared, the negative x squared like that is x squared. Negative x to the fourth power is just x to the fourth, and so on. Those do not change sign. And so what do we say about this function then? It's even, right? Because f of x and f of negative x end up being the same function. And then if you look at this function right here, let's say this one's g of x. So we can separate it out. So let's say we have g of x is, let's say, 3x to the fourth plus 2x cubed minus 3x squared plus 6, like that. Then when you look at g of negative x, on that one, every place you see an x, you put a negative x. Well, what happens there? The terms with the even powers don't change sign, because when you raise that negative number, like we just said, to an even power, right, you just get a positive. But there is an odd term in there. The negative x cubed is an odd term, and so that term does change sign, because negative x cubed is the same thing. If I cube negative x, I get negative x cubed, and so or the negative of x cubed. And so that term changes sign like that. The constant doesn't matter there at all. And so what happens, that function is not the same as the original function, and so this one is not even. Right? Because the function you end up with, g of negative x, is not the same as g of x. Right? If they're not the same function, then it's not even. All right, so on a test, I'm going to ask you, or on the test this week, on exam 1, I'm going to give you a graph, and I'm going to say, does this graph represent an even function, an odd function, or neither? And so you should be able to tell me whether it's, if it's even or not, based on the graph, whether it has symmetry with respect to the y-axis. I'll do the same thing with odd functions. But remember, the deal here is that odd functions, and let's put a kind of a vertical line through the page here so I can separate that. Here are my even functions right here. Here are the odd function stuff right here. Odd functions are symmetric with respect to the origin. And so remember, we did talk about this last week, so let's look at this one more time for odd functions and how they're symmetric. So this function right here, the first one I'm sketching, this is actually the cube function, and this is a kind of a classic example of an odd function like that, right? So this function is odd because this graph has symmetry with respect to the origin. So this is an odd function. Right? This function right here, let's sketch another one. Now, I'm going to sketch a graph that's kind of the same shape in some ways as the one we just did. Right, but notice this one does not go through the origin, and the quadrants don't work out right. So this one is not odd. Right? And then finally, let's look at one more. Let's say we have a function that looks like this. And this is an example of actually of a function that, for those of you who go on and take math, more math beyond college algebra, this is a graph that you're going to encounter next semester. This is an example of what we call the sine function. This is an example of a sine wave. And if you notice that graph does have symmetry with respect to the origin, that the quadrants match up, right? That this is the first quadrant right here, and notice whatever you have in the first quadrant matches up with whatever you have over here in the third quadrant, that those match up. And then the same thing is true for the second quadrant right here and quadrant 4 is that they match up. Right, as you rotate or as you pivot the quadrant around the origin, right, you get symmetric pieces in those opposite cornered quadrants there. Okay, and so that one does represent an odd function. So this is an odd function right here. So now I'm not going to give you anything too crazy, but I'm going to give you a graph and I'm going to say, hey, is this even, odd, or neither? Right? And most functions in general are neither. When you're looking at just the totality of functions altogether, most of them are neither. But you need to be able to pick out the ones that are even and odd, or be able to identify them at the beginning of a problem. Now the property, the equivalent property for odd functions that involves function notation that we saw with even functions is that f of x and f of negative x are not the same in the case of odd functions. They are opposites of each other. And so that's the one way to say that in Word, is that the functions are opposites. And actually, let me erase that. So I'll say it this way, that f of x and f of negative x are opposites. All right, so if you have f of x equals just x cubed, like that, then if you look at f of negative x, what are you doing? You're cubing negative x. And when you cube a negative like that, you get a negative sign in front like that. You get the negative of x cubed. And so notice that those two functions are opposites. And so this is an odd function right here. If we look at g of x, let's see. So g of x is, let's say, x to the 5th plus x cubed. Let's just say x to the 5th plus x cubed. Then g of negative x would be negative x to the 5th plus negative x cubed. And so both of those terms change sign. And since they both change sign, you end up with just the negative of x to the 5th plus x cubed. If all the terms change sign, if all of them change sign, then you have an example of an odd function, right? So this is an odd function also, right here. And then finally, if we looked at, I'm going to kind of squeeze this one in at the very bottom. If we have h of x is, let's say, x to the 5th minus 3, well, look, h of negative x is negative x to the 5th power minus 3. And the first term changes sign. That's the negative of x to the 5th, but the last term is a constant, and so it stays the same sign. And so that one is not odd, right? And so f was an odd function, g was an odd function, but h is not odd because not every term changed sign, right? Every term has to change sign when you're using that little test. All right, so this is what I'm going to do on the test is I'm going to give you, so on the exam, on exam 1, I'll give you a graph. And I'll say even, odd, or neither. Even, odd, or neither. Right? And then I will also give you an equation. And again, the same question, even, odd, or neither. So what do you do if you're given a graph? You know, if I give you a graph like this one right here, and I'm not going to, like I said, I'm not going to give you anything that's just crazy or anything, so don't get too panicked about this. I'm going to give you relatively simple graphs. So that graph right there, it has symmetry, but it doesn't have symmetry with respect to the y-axis. No. So does this graph have symmetry with respect to the y-axis? If you fold it on the y-axis, Does the graph fall on top of itself, right? Are there mirror images around the y-axis? And the answer there is no. So what does that mean, that it has no symmetry with respect to the y-axis? It means it's not even. Does it have symmetry with respect to the origin? Well, that's probably even more obvious, that the graph doesn't have these corresponding pieces around the origin and the opposite cornered quadrants there, and so no. And so this one is not odd. And so what's the answer here? So the answer on this graph is neither. Right? It's neither odd, even nor odd. All right, this graph right here. Let's say we have this is an example of a graph that we're going to encounter in a day or two. It's called an absolute value graph. And we are going to definitely talk about graphs of absolute value functions in a day or two. This one, does it have symmetry with respect to the y-axis? And the answer here is definitely yes. Now, can graphs have symmetry with respect to both the y-axis and the origin? Yes, they can, but if they do, then they are not going to be functions. And so you can't have a function that is both even and odd at the same time. That's not possible. You can have a graph that's even and odd, but not a function, not a graph that passes the vertical line test. So once you see it's symmetric with respect to the y-axis, then you're done, right? Then you've got symmetry. You have an even function right here, and you can finish. You're done with the problem. A function cannot be both even and odd at the same time. And then finally, so that's given a graph. Answer the question. And then if I give you a function, so like f of x equals, let's say we have x to the fourth plus 6x squared minus x minus 3. And then we have g of x is equal to, let's say we have x cubed times the square root of x squared minus 1. It seems complicated, but it's not going to be bad. So on the first one, if you look at f of negative x, you get negative x to the fourth power plus 6 times negative x squared minus negative x minus 3, right? Every place I see an x, I substitute negative x. And so now from what we've seen, we know that the even terms don't change sign, but the odd terms do, and there is an odd term in here, and this is plus x minus 3. And so this is f of negative x. So what do? You compare f of x with f of negative x. And the question is, are they the same? Are they opposites, or neither one of those? And in this case, it's neither one of those. They're certainly not the same function because the x term changed sign. And they're clearly not opposites because not every term changed sign. And so the answer on this one would be neither. Right? So this would be neither. All right, g of x. Let's look at g of x and see how that works. So we substitute negative x in place of x. Every place we see that. So like that. Every place we see an x, we put a negative x. So we've seen that the first term, that first factor, the negative x cubed, when you cube a negative, you get a negative there. So that's negative x, the negative of x cubed. Under the radical, that negative x squared does not change sign, so that's just x squared. And now compare the two functions. Here's g of x. Here's g of negative x right here. And notice that g of negative x is just g of x with a negative sign stuck in front of it. And so it is the case that they're opposites of each other because it's just got a negative sign stuck in front of it. And so this one is an odd function. All right, I will just give you a couple of problems. It's not going to be a whole bunch of them, but I'll give you a couple of problems, and I'll just ask you, is this even, odd, or neither? And I'll give you a graph and ask you that, and that you use symmetry to do that. I'll give you an equation and ask you the same question, and then you use this test where you look at f of negative x and see what happens. All right, so that's our discussion of even and odd again, and so that finishes that part of our lecture today. All right, so now we're going to move on to talking more with graphing. That's basically the way to look at this next part of our course, is more with graphing functions. All right, so what we're going to do today, first of all, is look at piecewise defined functions, what are called piecewise defined functions, and how, or what a piecewise defined function is, first of all, and then how we go about graphing them. So let's first talk about what a piecewise defined function is. So if you have a function that looks like this, it's kind of a strange, what appears to be a strange way of defining a function. But this is a classic example of a simple piecewise defined function. F of x is equal to 2x minus 3 if x is less than or equal to 1, and f of x is equal to x squared if x is greater than 1. So basically what you're saying here is that this function f is defined two different ways, and it depends on the x value that you have as to which function you're using. So for all x values where x is less than or equal to 1, this is the function we're talking about. F of x equals 2x minus 3. For all x values where x is greater than 1, then we're talking about this function, f of x equals x squared. Right? So you have a function that's actually defined several different ways depending on the domain value that you have, or the input value you have. There's actually lots of examples and applications of a piecewise defined function. An income tax table is a perfect example, perfect simple example of a piecewise defined function, because it depends on your income, and the income is given in terms of ranges. And for every income that you have, your income tax is a certain level. And so it's a perfectly good example of a piecewise function. So for this problem, if I was looking at f of 6, well, what's the x value here? Well, the x value is 6. And so that is greater than or equal to 1, right? In this case, x is greater than 1. And so what function am I using for f of 6? I'm using f of x equals x squared is the definition. And so f of 6 is 6 squared, or 36. Right? If we were looking at f of negative 10, in this case, the x value is negative 10, and x is in the category of x less than or equal to 1. And so what do we do here? We use the function f of x equals 2x minus 3 to evaluate this one. And so f of negative 10 would be 2 times negative 10 minus 3, or negative 23. Right? So it depends on the x value that you have as to which function you're using. So in this problem, f of 0, you have f of x is 2x minus 3 is the function we're using, right? And so this would be because x is less than or equal to 1. So this is 2 times 0 minus 3, or negative 3. F of 1 fits in the category that x is less than or equal to 1, right? So that's the case for both of these examples right here. And so you're using that first function. And so you get 2 minus 3, or negative 1. But f of 2, now you're talking about x greater than 1. Right? So f of 2 would be just 2 squared, or 4. Right? So you have to go based on the x value as to which function you're using, right, when in the problem. So let's look at another example. Let's look at g. So let's say the g is negative x if x is less than or equal to negative 2. It's equal to 3 if if negative 2 is less than x, which is less than or equal to 1. Okay, and it's equal to the absolute value of x if x is greater than 1. So this function has 3 pieces to it, and it depends on what the x value is, right? If the x value is less than or equal to negative 2, you use negative x. If the x value is between negative 2 and 1, including 1, then you use the constant function 3. And finally, if the x value you're using is greater than 1, then you just use the absolute value of x. All right, so g of negative 3 then, that x value is less than or equal to negative 2. And so you use the first function, and you have the negative of negative 3. And so that would be positive 3. If you have g of negative 1, and so in this case, the x value is between negative 2 and 1, right? So that means you're using the middle function. And the middle function, in this case, that middle one is just 3. It's a constant function, and so g of negative 1 is 3. G of 0, because that's a constant function, would be 3. G of 1, because it's a constant function, that would be 3, right? In all those cases, the x value is between negative 2 and 1. G of 0.7, because that x value is between negative 2 and 1, you get 3. And then finally, something like g of 10. In this case, the x value is greater than 1, and so g of 10 would be equal to the absolute value of 10, which is just 10. Right? And so that's how you evaluate a piecewise defined function. So that's the first thing we need to do, is just talk about how you actually evaluate a function like that. And so now let's talk about actually graphing piecewise functions, which can be a little bit more tricky. So graphing piecewise functions. All right, so let's say we have, let's start off with this example. F of x is equal to x plus 3 if x is less than 0, and it's equal to negative, let's say, negative 2 minus 2x if x is greater than or equal to 0. Okay? So if we're talking about graphing this kind of function, then this is the way I usually look at this kind of graph. Is that what you have is the plane divided up into, in this case, into 2 pieces, and they're divided at x equals 0, because that's the break in the domain. You have x less than 0 and x greater than 0. And so there's a dividing line here in the domain, and it's on this dashed line right here. And what do we have? That to this side, to the left of that dashed line, you have x less than 0, and on the right side, you have x greater than 0, like that, right? And so that's where the domain is broken up in this particular problem. And then what do we have here? We have that f of x on the left side of that line, when x is less than 0, is the function x plus 3. And on the right of that line, you have f of x is equal to negative 2 minus 2x. And so what I'm going to do is I'm actually going to make a t-table for both of these functions off to the side over here. And we're going to actually plot points for each one of these. Now you have to be careful. On the first function, it's defined to be f of x equals x plus 3 only for x values less than 0, right? You've got x less than 0 there. And on this one over here, you've got x values greater than 0, greater than or equal to 0. So now what you do, and I know this looks kind of weird at the beginning here, is you automatically put 0 as x's for both of those functions in both t-tables. Now, I know it's not defined in both of those t-tables. That's okay. Don't worry about that. You automatically put that dividing x value into both of those t-tables. Always do that. Not just for this problem. Just always do that with a piecewise function. And then you pick more appropriate x values for both of them, or appropriate x values for both of them. So on the first one, it's got to be x values less than 0. So you might pick -1 and -2. You have to pick x values less than 0. And on the other one, you have to pick x values greater than 0, so maybe I'll pick 1 and 2. Now, in both cases, these are linear functions, and so the graphs are both going to be lines for both of these, so you really only need 2 points for both of them, but I'll put 3 in for both of them. Just fill out the tables now. So this one would be 0, 3. Put -1 in place of x, remember, so you have -1 plus 3, so that would be 2. And then -2 plus 3 would be 1. All right, so you have the points 0, 3 right here, and then -1, 2, and then -2, 1. So you get those points, and you're clearly getting a line right there. Now, so you're getting this line for this graph. Now, as the graph comes up to this point 0, 3, we note here that x has to be just strictly less than 0. And because x is less than 0, not less than or equal to 0, but just less than 0, you actually put an open circle there at the end of that graph to say that that point's really not part of the graph right there. And so you put an open circle there. If it says x is less than or x is greater than, then you're going to have an open circle on your graph like that. If it says greater than or equal to or less than or equal to, you're going to have a filled in dot. All right, so let's do the other function. The other function, fill out the t-table. When you put 0 in place of x, you know, you have -2 minus 2 times 0. So that's just -2. And then you put in 1. So you have -2 minus 2 times 1. That's -2 minus 2, or -4. And then you put in 2. You have -2 minus 2 times 2 is -2 minus 4, or -6. And so if we plot those points, you have 0, -2, which is here, and then 1, -4 here, and then 2, -6 down there. So this graph is also clearly a line. The graph's coming in this way. But what happens is it gets up to this point 0, -2. That point is actually part of the graph, and that's a filled in dot. And again, because that says x greater than or equal to 0 right there. Right? And so that's your graph right there. And the graphs on these are going to look kind of interesting because they're going to actually be pieces of graphs like this. Also, always look back. Always look at your finished graph on these kinds of problems and ask, does my graph pass the vertical line test? Right? Very common for students to incorrectly sketch these so that the pieces overlap each other. And that can't happen if you have a piecewise defined function. See, so on this graph, I frequently will get people to kind of sketch it so it looks like this. And so they'll get these pieces, but the pieces they'll extend the pieces like this and extend the pieces, and they'll get something crazy like that for the graph. Right, those pieces overlap each other, and so that graph fails the vertical line test, right? And so these are functions, and so the graph cannot fail the vertical line test. It has to pass the vertical line test. And so you've got to always look at your graph and ask yourself that question. All right, so let's look at another example. Let's say we have g of x is equal to, let's say we have 2 if x is less than negative 1. So g of x is equal to negative 2 if x is less than negative 1. It's equal to x squared if negative 1 is less than or equal to x, which is less than 2. And then finally, it's equal to, let's say we have 3 minus x if x is greater than or equal to 2. So this particular piecewise function has got 3 pieces to it. So the first thing we're going to do here is we're going to divide the plane up into sections or chunks here based on where the breaks in the domain are in this graph. And where are the breaks in the domain? The breaks in the domain here are at x equals negative 1 and at x equals 2 based on those definitions. And so what am I going to do? I'm going to put a vertical line here at negative 1. That's at x equals negative 1. These vertical lines are not part of the graph. They're just tools to help us sketch the graph here. And then there's another break in the domain here at x equals 2. Right? And so this plane is divided up into 3 sections. And the 3 sections are where x is less than negative 1, where x is between negative 1 and 2, and then finally where x is greater than 2, greater than or equal to 2. All right, so what do we have here in the first section? We have the constant function g of x equals negative 2. And then in the middle function here, I'm going to put this one below the graph just because there's no room to put it at the top there. This one is g of x equals x squared down here. And then finally, this function on the far right is g of x equals 3 minus x. All right, and what are we going to do here? We're going to make t-tables for both of these, or on both of these, all 3 of these. And plot some points here to make a correct sketch of the graph. So in this first one, g of x equals negative 2, I'm going to put negative 1 in that t-table right away because that's the boundary point there, the boundary x value. I'm going to put negative 1 in for x squared also. And I'm also going to put in 2 for x squared because I've got to put both edges on there. And then on this last one, 3 minus x, I know I've got to put 2 into that one. And then you pick other appropriate x values. So on the first one, g of x equals negative 2. The x value has to be less than negative 1. And so I'll pick another one like negative 2. For g of x equals x squared, I know the x values here have to be between, right, negative 1 and 2. I've already got negative 1 and 2 picked, so I might pick 0 and 1 also there. This is g of x equals x squared, and so it is not going to be linear. The graph is not a line. And then finally on this last one, x has got to be greater than or equal to 2. So I've got 2 in the chart already, so let's pick 3. And it's a linear function, that's really all I need. All right, so let's finish those t-tables up. So on the first one, this is a constant function. So g of negative 1 is negative 2, and g of negative 2 is negative 2, right? The y value is always negative 2 there. On that middle function, you've got x squared, and so, this is negative 1 squared, so that's 1. This is 2 squared, so that's 4. This is 0 squared, so that's 0, and this is 1 squared, so that's 1. And then finally, g of x equals 3 minus x. You have 3 minus 2, which is 1, and 3 minus 3, which is 0. So you've got those 2 points. All right, now we go in and plot these points. You just have to be careful as the graphs get into those vertical lines, those places where the pieces are separated. Make sure that you're careful about whether you have a solid dot or an open circle. So in the first graph, g of x equals negative 2. I've got negative 1, negative 2, which is here, and negative 2, negative 2, which is right here. And so we've got the graph as this horizontal line coming off like this. Constant functions are always horizontal lines, by the way. Constant functions are always horizontal lines. But the restriction is that x has to be less than -1. So this is an open circle here at the end. And so here is my graph with that open circle on the dotted line right there. And then you have g of x equals x squared is that middle function. And so you have -1, 1 is this point. 0, 0 is here. 1, 1 is here. And then 2, 4 is up here. But what do you have? That -1 is, this says x is less than or greater than or equal to -1. So this is a solid dot here. But x is less than 2, so this is an open circle on this one. And then you've got this parabola sitting in between here like that. And so that's the graph of the middle piece right there, is that piece of the parabola. And there's a solid dot on one end and an open circle on the other end. And then finally, g of x equals 3 minus x. You've got the point 2, 1 here and 3, 0 here. You're getting a graph as a line like this, slanted downwards. But at 2, 1, the graph is actually defined there because it's x greater than or equal to 2, and so that's a filled-in dot right there. And so that's the sketch of this graph. It's kind of a crazy sketch, right? It's 3 distinct pieces, and those vertical lines are just put in there to help you divide up the pieces there and to divide up the functions more than anything else. If you choose not to use those vertical lines in there, that's okay. As long as you can keep the x values straight as to which function you're talking about, that's all I'm looking for. I think putting those vertical lines in there is helpful to help you separate the pieces out. Notice that on the vertical lines, on like for example, the one on the left here, notice that that one's filled in, but this one's open right here. And notice that they can't both be filled in because then the graph would fail the vertical line test. So notice as they both come up to the graph, typically what's going to happen is one of them will be filled in and one of them will be an open circle, right? And that's because the graph has to pass the vertical line test. Now they could both be open, but they can't both be closed. They can't both be filled in. That's not possible. All right, so that's a kind of a good solid introduction to piecewise defined functions. This last one here on this page is about as complicated, certainly as complicated as you would see. And so that would be as hard as a test question as you could get. And this is not simple. You have to be careful about how you're sketching the graph. There's no question about that. All right, so the last part of lecture today, we're going to start looking at what we call function transformations. And this is going to be function transformations part 1 is what the way I'm going to term it. And then we will next time on your calendar, we have linear functions listed as what we're going to cover next time in class, which is what we'll do. But we'll also cover function transformations part 2 there as well. And we'll kind of lay the groundwork for part 2 as we go through what we're going to talk about today. All right, so a transformation, first of all, there's the transformations are divided up into kind of three groups is basically the way I would look at it. We have what are called the shifts. That's one type of transformation. And shifts are actually divided into 2 types of shifts. We have vertical shifts and horizontal shifts. Right? So we're going to talk about shifts and how that relates to graphs. And that's a type of transformation. We have the reflections. And there are 2 types of reflections. There's reflections around the x-axis and reflections around the y-axis. And then finally we have what, you'll see this a lot of different words here. We have changes in shape. And the changes in shape that we're going to look at what are called stretches and compressions. Basically, these are all ways that you can modify a graph. You know, is one way to look at this. So if we look at a typical graph like this, let's say, and we're going to start off with some relatively simple graphs. So let's say we have a graph that looks like this one right here. That's our function f right there. Now, if we take that graph and we literally take the graph off of the screen and simply shift it to the right or to the left. So here's the original graph, but I simply shift it. Right, what have I done with the original graph? I've shifted this graph to the right. And how many units have I shifted the graph? All you're doing is literally counting, but if you just count, it's just 4 units, and it's a shift right 4 units is what you did right there. And so this is what we call a shift of the graph, and this is what we call a horizontal shift of the graph. So this is a horizontal shift. Right, where you take the original graph and you simply shift it to the right or to the left. And so this is a horizontal shift, and this is right 4 units. And if we take that same original graph, so I'm going to again sketch here. And here's our graph. I'm going to make the original graph dashed here. And then I look at this graph right here. What happened there? I took the original graph and I shifted that one up. Right, that one went up, and it went up 2 units if you count. Right, and so this is called a vertical shift. And this is up 4 units. And obviously vertical shifts can be up or down. All right, so this is what we're talking about with shifts. All right, so we're going to look at how you get these in a few minutes. But I just want to look at some examples of each of these pictures, okay? All right, so now if I continue with that same graph, so this was our original graph right here. So let me sketch that one more time. That's our graph like that. And I go ahead and, so I'm going to sketch that one again. In fact, let me go ahead and copy this one so I don't have to keep on sketching it. So I'm going to copy it and paste it a couple of times. So paste one and put it, have to line it up. And I guess that one is not quite lined up like I wanted to, so let me line it up again. It has to line up with the grid that I've got on the paper. Paste one there. Paste another one there. All right, so if I take that same graph and let's see, I'm going to use a different color here. And I take that same graph and I literally flip it upside down. So this is the new graph right here in green. This is called a reflection, and this is a reflection. I've literally flipped the graph around the x-axis. So this is called a reflection around the x-axis. On the other hand, if I look at this graph right here in green, right, if you notice that one, I've reflected that one. I've literally flipped it around the y-axis. And so this is an example of what we call a reflection around the y-axis. like that. Finally, let's, so those are examples of reflections and what reflections look like. So now if I take this original graph, this last one's a little bit maybe harder to see, but if I take my original graph, which is that one right there, and let me sketch it again right next to it. I'm just going to go ahead. I didn't really like the way that cut and paste worked on this one, so I'm just going to do this dashed here. So here's my original graph. And then let me do that one more time down here at the very bottom. And here's my original graph. I like to put the original graph as kind of a dashed line so it kind of separates out from the new graph. If I take those points and I literally kind of pull them away from the x-axis. So for example, on that first graph, if I take the points that are off of the x-axis and I pull them away from the axis, and notice I pulled both of those points 4 units away. They were 1 unit away, and now they're 4 units away. And the point that's on the x-axis actually kind of stays put, like that, because you're pulling every point that's the same number of units. What you're actually doing is multiplying to pull them away from the axis. And this is our new graph right here. This is an example of a stretch of the graph. You're stretching it away from the x-axis. So now notice some of the points actually that are close to the x-axis stay there, but points that are further away, you get pulled further away. And so this is what we call a vertical stretch. Technically a vertical stretch. I'll usually just call it a stretch. And then if we take the same graph, now this one's harder to see, and I smush the points closer to the x-axis. So this one's really harder to see here. Like that. That one's in green there at the very bottom. So everything's getting pushed in closer to the x-axis. This is called a vertical compression. You're really compressing the graph closer to the x-axis. Now, I'm not going to look at horizontal. You can also look at horizontal stretches and horizontal compressions. I'm not going to do that type of transformation. We're just going to look at vertical stretches and vertical transformations. Okay, so those are all pictures that show you the different kinds of transformations we're going to look at. So the question is, how do you know when you get those various types of transformations in a function statement? So what we're going to do is we're going to start off with another function. We're going to use another basic function here. We're going to draw something different. So let's say I have a semicircle. And that semicircle is right here, located in this point, and it's the upper half of a circle. So pretend that that's the upper half of a circle right there. And that's the graph of my function f. All right. Then the shifts of the graph, the vertical shifts, or I'm sorry, just the shifts in general. Let's do it that way. You have two kinds of shifts. You have vertical shifts and you have horizontal shifts. So a vertical shift are given by taking the original function and either adding or subtracting a constant. And we'll just say that the k value is positive throughout this from the function itself. So if you have f of x is plus k is a positive number here, then this is a shift up k units. And if you have f of x minus k, this is a shift down k units. And the easy way to think about this is remember that f of x and y represent the same thing. Whenever I write down f of x somewhere, I'm really writing down y. And so notice when I write f of x plus k, I'm really just saying take the y value and add a constant to it. And if I'm saying f of x minus k, I'm saying take the y value and subtract a constant from it. So those are the vertical shifts. And then the horizontal shifts, so on this page, we're just going to look at shifts here. Horizontal shifts, you get those by taking the k value and adding it or subtracting it from the x value. So in other words, f of x plus k or f of x minus k. If you have f of x plus k, this is a shift. Now this is going to seem kind of backwards, but this is a shift to the left k units. And if you have f of x minus k, this is a shift to the right k units. We'll talk more about why it looks backwards there later. All right, so here's my function f of x. I've got this basic function that I've given you. That's kind of that semicircle right there. So I'm going to sketch that semicircle again, right here. Whoops, but I'm going to make it dashed, like that. So there's f of x. So what I want to do on this page, right, or on this little coordinate system right here, is I want to sketch the graph of f of x minus 2. F of x minus 2. So based on what I've written down on the side, right, you're talking about taking the y value and subtracting 2 from it. You're literally taking every point on this graph, taking the 2 and subtracting it from the corresponding y value. And what happens is you end up with the exact same graph, simply shifted down 2 units. And so that's my vertical shift right there. Let me sketch maybe slightly better. Slightly better. So that's f of x minus 2 right there. All right, if I do the same sketch, the same graph, so here's, once again, f of x. Here's my basic graph. And I remember, this is something I gave you at the beginning of the problem. So there's f of x right there. And I want to sketch f of x plus 3. So this would be shifting the graph vertically 3 units up. So this is up 3 units. You're adding 3 to each y value. So you're literally counting each point on that graph. You're literally just counting up 3 units. Right? You're literally adding, and you could actually sketch that in there if you wanted to, that's what you're doing here, is every point is simply going up 3. You're adding 3 to every y coordinate. Now, if you start drawing all those arrows in like that, it gets confusing. So we're certainly not going to do that all the time, but that's what's happening there. You're adding 3 to the y coordinate there. All right, next one I want to look at here. You can actually kind of fit one in here at the bottom. So again, here's my basic function, right? All these are related to this original basic function that I gave you at the very beginning of the problem. And so now what I want to do is I want to sketch f of x plus 3, like that. So it's f of x plus 3. So now notice what the difference here between that one and the one before it. Notice in the one before it, I'm adding 3 to the y value, because this is y plus 3, right? This is really y plus 3. So I'm adding 3 to the y value. Here I'm adding 3 to the x value. And what happens when you add 3 to the x value is you actually shift the graph to the left that number of units. So I'm shifting the graph to the left 3 units. So you're counting 3 units to the left. Every point gets shifted to the left 3 units. And here is my new graph right here. And that's the graph of f of x plus 3. One way to look at this is, if you're thinking about y that's a shift to the left, simply compare f of x and f of x plus 3. So how would you get, if x was 0 here, right? That's if x is 0, you have f of 0. Well, how do you get 0 in the second statement inside there? What has to be true here is that x has to be negative 3, and that would give you f of 0 in that one. And so what happens, on the original function, 0 gets shifted back to x equals negative 3. It gets shifted in the opposite direction is the way to look at that. All right, let's look at this last one here on this screen. So let's say that we, again, here's our original function. Put in this is the function, this is our basic function, right? And so I would have to give you that graph at the beginning. And so that's something that you'd be given. And so that's the original graph is my basic function. And let's say I want to sketch f of x minus 1 plus 3, or plus 2, let's say. So sketching f of x minus 1 plus 2, this is a shift to the right 1 unit, but it's also a shift up 2 units. This graph has both a horizontal and a vertical shift in it. So you're literally counting, and you're literally counting right 1 and up 2. Now I'm just going to do that for 1 point here to show you. So you're shifting to the right 1 right there, and you're shifting up 2. And that would be the new point for that graph where it gets shifted to. Right 1 and up 2. And every point's the same. And so here is my new graph. There's my transformed graph right there. All right, so that one actually had both shifts. All right, so I think we're doing okay here. No one's really yelled at me through for those of you who are watching live. So either you are completely lost and you have no idea what I'm talking about, or you're kind of sort of following this. This is something, function transformations, that we're going to fall back to frequently during the semester. So this is not the only time we're going to cover this. We're going to come back to it over and over again during the semester. And so you'll get used to this, hopefully, as we go through this. The reflections. Here's my basic function right here. The reflections are somewhat easier. There's not too much to take care of there. You either have the negative of f of x. This is a reflection around the x-axis, or you have f of negative x, and this is a reflection around the y-axis. And see, the negative f of x, you simply are saying, remember, what does f of x represent? F of x is y. So when you stick a negative sign in front of the function, you're really saying, when you say negative f of x, you're really saying take the opposite of the y value. And that's exactly what you're doing. You're taking the opposite of the y value. You're changing the sign of the y value. Change sign of y value. That's really what you're doing. So you take every y value and you change its sign. If it's the other type of reflection, you change the sign of the x value. Change the sign of the x value. And I think I spelled the word sign incorrectly there. Okay, so let me try that one more time. There we go. Change the sign of the x value. All right, so on my sketch right here, if I ask you, the original function remembers f of x right there. So if I say sketch negative f of x, well, negative f of x is a reflection around the x-axis. You're changing the sign of every y value. And so the new graph is simply flipped upside down is one way to look at it. And you actually see some people describe this as a flip around the x-axis. And so here is negative f of x right here. Negative f of x is simply the original graph reflected around the x-axis. And if we take our original graph, and here's my original graph right here, and I say sketch f of negative x, then this is saying change the sign of all the x values on the graph. So you take every point, and you could literally do that then. You could take this point 4, 2, and you simply change the sign of the x value on that point. I'm sorry, that's not 4, 2, it's 4, 0. I don't know why I said 4, 2. That's better, 4, 0. And so then you change the sign of the x value there, and you get negative 4, 0. Like that. Right, so that point reflects to the other side of the y-axis. And all the points do the same thing. And there's my reflection around the y-axis, like that. Right, you get a corresponding point on the other side of the y-axis. All right, and let's see. Let me sketch in the changes in shape. We'll do those, and then that will finish it. So those are the reflections. The changes in shape are called the stretches and compressions. The stretches, you get those by taking a constant, and multiplying it by the function, and that constant has to be bigger than 1. And if that constant, remember we're talking about this constant being positive, and if the constant is less than 1, so in other words between 0 and 1, then you get what we call a compression. And we won't look at compressions probably quite as much, but let's look at a stretch here, and then that will finish what we're going to do for the day today. So here's my original graph again. So we're going back to my basic function that I gave you at the beginning of this example, or this set of examples. There's my basic function, f of x. And I say sketch 4 times f of x. Then that literally says multiply each y value by 4. Right? That's what you're talking about doing. Multiply each y value by 4. So you just take every y value on that graph. So like this point right here is at the point 3, 1. You take the y value and you multiply it by 4, and you get 3, 4. But this point right here, which is at 4, 0, you multiply that y value by 4, and you still get 0. And so you get this graph right here, and you can see that this graph has kind of been stretched away from the x-axis, right? Been stretched away from the x-axis. And so that's what the graph looks like right there. All right, so we've looked at graphing piecewise functions. So let me just write down textbook practice on all of this stuff. So textbook practice. And then we will be finished with the day. So we are operating in chapter 3. And we're actually in sections 3.2 and 3.3. So in section 3.2, we talked a little bit, and these are problems I had not really given you yet. These are piecewise functions in section 3.2. So this is practicing piecewise functions, and so this is on page 194 of your textbook, problems 39 through 49 odd. Right, so that's practice on piecewise functions. And then on even and odd functions, I think I'm going to have to I don't know, I'm going to have to search in the book for that. So I'll go back and look at that. And I think I've already given you even and odd functions. I think I just missed it in the book. So, all right. So this is on piecewise functions right here. All right, and so like I said, I'll search to see if I can find in the textbook something having to do with even or odd. Actually, I just did. This is on, so even and odd, this is on page 277. And this is problems 15, 16, and 17. And that's even, odd, or neither. And so that'll give you a little bit more practice on that. I've already done a little bit with giving you practice on that, but that's a little bit more practice. So, all right, any of you have any questions for me?
I'm good.
All right, we're Ashante? All right, then if there's no question,